everyone, my name is Sajjad Hussain and I have completed my bachelor's in computer science and engineering from East West University. This task was given by DataSynthis and it focuses on understanding some important algorithms and data structures used in distributed systems and machine learning. In this presentation, I will explain four main questions which was given by DataSynthis. Now let's begin. First, here is the question number one. We can see that outline an algorithm for finding a minimum spanning tree in a distributed system. There is also a follow-up question. In what real-world ML scenario would you use MST, such as sensor network or feature selection? My answer is what an MST. Let's begin with that. A minimum spanning tree is a subset of edges that connects every node with the smallest possible total weight and no cycles. In a distributed system, the graph data is partitioned across multiple machines. Therefore, the goal is to design an algorithm that performs most computations locally and minimizes inner-machine communication. The algorithm that fits these settings best is Borakrav's algorithm. It is inherently parallel in each iteration. Every component independently selects its cheapest outgoing edge. These edges are then shared across machines, merged into the global MST, and the connected components are contrasted. This process repeats until a component merges into one, forming to complete minimum spanning tree. Because multiple components merge in each round, the number of rounds is logarithmic in the number of nodes, giving excellent scalability for distributed environments. Let's visualize with the two machines, machine A and machine B. Machine A holds a subset of the graphs. Here is three nodes A, B and C. Also, machine B holds another subset with the nodes D, E and F. Now each machine locally computes its cheapest ongoing edge. Machine A selects edge AB with weight 2. On the other hand, machine B selects DE with weight 1. These selected edges are reported to coordinate merge into the MST and components are updated globally. And this process continues until all nodes are connected through the minimal edge, forming the distributed MST. Now let's focus on the pseudocode. First, we will begin with the edge vertex as its own component. On every machine, the minimum weight outgoing edge from each local component. Send these selected edges to the coordinate or reducer node and all valid edges to the MST. Merge the connected components and synchronize components ID across the cluster. Repeat this process until one global MST remains. Here is the complexity and the trade-offs. Where local communication proportional to the number of local edges. Communication only minimal edge summaries exchange per round. Roughly O log V due to progressive component merging. Trade-offs achieves strong parallelism and low communication cost but requires synchronization for component levels. Now we will go for the follow-up questions. In what real ML scenario would you use MST? My explanation is so MST or minimum spanning trees are actually very useful in real-world machine learning and data system scenarios where we need to connect things efficiently without redundancy. Let me give you a few examples. First, sensor network optimization. Imagine we have thousands of sensors spread out in a field or factory. We want them all connected so data can travel between them, but we also want to minimize the total communication cost or power consumption. Here an MST helps by connecting all sensors with the minimum possible total distance or signal cost, no cycles, no wasted links. Secondly, feature selection in machine learning. When we have a large number of features, some of them might be highly correlated or redundant. We can represent each feature as a node and the edge weights as their pairwise correlation. Building an MST helps us choose the minimum set of features that were well connected but not overly redundant, kind of like finding the backbone of the feature space. Thirdly, the clustering. In clustering, MSTs are used to find relationships between data points. For example, if we build an MST overall data points and then cut the highest weight edge, we can get clusters. This approach is used in algorithms like single linkage clustering. Lastly, distributed gradient aggression in ML systems. In distributed training of models, gradients or parameters are shared among multiple machines. MSTs help minimize communication cost by connecting servers efficiently, forming a minimal spanning communication structure. Now let's focus the question number 2. In the question number 2, given a large system of user interactions, design a data structure for O log n, range sum queries and updates, supporting both exact and approximate aggression for downstream feature generations. Also a follow-up question: how do you parallelize updates for distributed feature stores? For supporting both O log and range sum queries and point updates efficiently, the ideal data structure is the Fenwick tree, also known as the binary index tree. A Fenwick tree maintains prefix sums in a compact array structure. Both updates and prefix sum queries operate in logarithmic time, making it ideal for continuous streaming data. To compute a range sum L and R, we simply calculate prefix R minus from prefix L minus 1. In large scale or distributed systems, we share the data. Each shared maintains its own Fenwick tree. Global queries are computed by aggregating results across shares. Here is the short visualization of the Fenwick tree. Now let's focus on the pseudocode. First, we initialize a bit array of a size n+1. Then for each event, for example a user click or interaction, call update with its index and value. Then to answer a range query, call range sum LR, which internally performs two prefix sum calls. In distributed systems, divide the index space into shards and each operation, query all relevant shards and combine their partial sums. Here is the complexity and the trade-offs. And the follow-up question: how would you parallelize updates for distributed feature stores? When we talk about distributed feature stores, so we are really talking about systems that keep track of user or item feature things like user activity counts, purchase frequency, or embedding vectors across many machines. Because updates come in as a continuous stream of events, we need a way to apply updates parallel without breaking content consistency and accuracy. Here is how we can parallelize it step by step. First, partition the data. First, we divide the feature space, for example, by user id, item id, or hash range, and assign each partition to a separate machine. This means updates for different keys go to different shards and can be processed in parallel. For example, if user IDs goes from 1 to 1 million, shard 1 handles to 1 to 200k, shard 2 handles 200k to 400k, and so on. This reduces coordination overhead and keeps each node workload independent. Then use the local data structures like local fenwick trees or segment trees. Inside each shard, we maintain a local data structure like a fenwick tree or segment tree for fast updates and queries. Since each shard handles its own portion of data, updates within it can happen concurrently using thread safe operations or batching. Then batch and system updates. Instead of processing every update immediately, group small updates into micro batches, such as every few seconds or a fixed number of events. This amortize overhead and allows efficient disk rise or in memory aggression. Streaming platforms like Kafka, Flink, or Spark streaming are commonly used to orchestrate this batching and parallel update flow. And then March partial aggregation. So in a global query like total clicks in the last hour is indeed we aggregate partial sums from all shards. Each shard computes its local value, then a coordinate node merge the results like a reduce operation in a map reducer. This keeps a global queries scalable since each shard works independently. Then handle consistency and dependency. To ensure correctness, especially when the same update might be replayed, make updates idempotent, meaning applying the same update twice doesn't change the result incorrectly. Example: use versioned timestamps or automatic increment options. And the lastly, optional use approximate structures for speed. For extremely large scalable features like tracking millions of events, use approximate mergeable data structures such as count, min, scratch, approximate frequency counts that can be merged across shard, hyperlog, approximate unique counts. This can be merged by summing or combining hash tables, allowing parallel computations with minimal data exchange. This is the visual representation of the how Kafka, how a streaming platform works. share their data. Uh, Now let's focus on the question number 3. You are tasked with designing an ML model cache. Explain how a split tree helps optimize across patterns and what the trade-offs are compared to LRU. Caches. The follow-up question is when would displaying harm latency in serving predictions? A split tree is a binary search tree that spells or rotates any accessed node to the root. That means if some items are accessed often, they will stay near the root and be cheap to the access again. This is good for squid non-uniform access patterns compared to a standard LRU cache hashmap plus linked list. LRU gives a constant time operations and recency semantics, while display gives adaptive behavior but with having operations on access. If access is a random or you have strict tail latency, the rotations of display can actually hurt in the setting of LRU or segmented is safer. Here is the diagram of a split tree. Now focus on the pseudocode. When a model or data entry is requested, perform a BST search. If found, split tree display it to the root, ensuring faster access for future request. If not found, load it from persistent storage, insert into the tree, and split. For eviction, remove the deepest or least useful node based on cache limits. Then here is the follow-up question: when would displaying harm latency in serving predictions? Displaying can actually become a disadvantage when the access pattern to the model cache is highly repetitive or predictable. Here is why a split tree recognizes itself every time an element is accessed, moving that element to the root through multiple rotations. This is helpful when access patterns are irregular because frequently used items automatically move closer to the top. But in real-world ML serving systems, such as an API that repeatedly requests predictions from the same model or retrieves the same cached result, this self-adjusting behavior adds unnecessary overhead. The same nodes are rotated again and again, even though they are already near the root. As a result, these repeated rotations waste computation time and increase latency, especially in systems where predictions responses need to be delivered within milliseconds. In such stable workloads, a simplified cache structures like least recently used or cache or a hash map using actually perform better because they don't pay these rotation costs. Now the question number 4 and the last question. Build a system to support efficient merging and querying of connected user components in a social graph as edges are added or deleted for clustering in ML. The follow-up question is how does union by rank and path comparison speed up large-scale ML graph operations? To maintain connected components efficiently, we use a union find disjoint set union. Uh, each node has a parent pointer, and find climbs up to the root, which is the component representative. With path comparison, we flatten the path during find, and with union by rank, we keep heights small. Combined each these optimizations give almost constant time operations in practice. This is the standard technique for the clustering and the preprocessing of graphs in ML. If edges are detected frequently, union find alone doesn't handle it well. We need dynamic connectivity structures of prediction rebels. uh, Here is the pseudocode. For each new edge we call uh, UV. To check connectivity of U and B, call find U, find B. Use path comparison inside find, so repetitive lookups become fast. Handling deletions brief. If edges are deleted often, classic union find fails to split components. Options: use reveals on many deletions, recompute components from scratch. You use dynamic connectivity data structures, Euler tool trees, linked trees, more complex but support deletions and connectivity queries in polylog time. In follow-up questions, in how does a union by rank and path comparison speed up large scale machine learning graph operations? In large scale machine learning systems, think of social graph clustering, friend recommendation, or community detection. We often need to repeatedly check with users are connected and efficiently merge those connections. If we use a native union find structure, these operations could become quite slow because trees might grow very deep, making find operations costly. That's where two key optimizations come in. Union by rank ensures that we always attach the smaller tree under the larger one, keeping the structure balanced and shallow. Path comparison patterns the structure even further during each find operations by making every visited node directly point to the root. The combination of these two techniques drastically reduce the effective complexity nearby constant time, like O alpha n, where alpha n is the inverse Ackermann functions, which is particularly constant for all real world datasets. In machine learning, this optimization allows us to handle millions of nodes for edge efficiently, making union find ideal for dynamic graph when new relations or clusters are continuously formed, like social networks or item similarly graph. uh, that's all from my end. Thank you.